Hello students, this is Professor Bell, and I wanted to get you started for the semester with this lecture video about science and geography and how we know what we know about certain things. So I'll just lay out for you real quick about what is a fact, hypothesis, and a theory. And so I won't belabor it since you can pause this and read it, but essentially a fact is something that we can, of course, observe and measure and understand. For instance, we've got the example of lightning and being able to measure temperatures accurately now. So, it's pretty straightforward. A hypothesis, of course, is a logical guess, but with, of course, information based on the guess. So it's an informed guess. And then how do we look at it in science? How are we able to measure this and then test it? And so to have a good hypothesis means you have to have a good question, a good geographically relevant question. For instance, about the ecosystem, as you see in this example, about aphids, if they thrived after ladybugs were introduced. But if you leave that kind of out, how do you measure, how many ladybugs did you put on the flowers to eat the aphids, things like that. I don't know if I'm doing a good job of it here, explaining it, but as we look, these things are not interchangeable. And a fact, you don't have the right, for instance, to your own facts. You can't just make something up is really what we're talking about here. And then for a hypothesis to work, you'd have to have enough information about it to make that logical stab and then be able to test it. And then, of course, building a reliable test is paramount, and that it can be replicated by others. Some of this is left out. I don't know if you understand how science gets done today, but I'm about to show you some of it. Anyway, when we look at truth in science and say it's a theory, it's not the layman's sense of theory. Hey, I got a theory about why the light doesn't work. It's unplugged, the bulb is shot, electricity went down, the whole neighborhood's dark. Those are getting to the point, but when we look at a scientific theory, we can't watch evolution happen. We can actually now watch plate tectonics happen. Plate tectonics goes at about the rate, the plates themselves are moving about as fast as your fingernails grow. Collect your fingernails for a year and see, how much the continents move. But that said, we may not be able to witness it firsthand, but we can build models that would test based on that information, and have this community of scientists that are able to check each other and peer review stuff. So when we talk about, for instance, climate change, we know that there's a natural aspect to it, but we certainly know that humans are the driving aspect behind it. And so, we'll cover some of these things in the semester, looking at these things. So when we look at these impacts, external and external forcings with effect, and what is the response? So again, we look at the climate, and that's going to consume us in the first half of this semester. We look at our agriculture, cutting down forests, rainforests, deciduous and otherwise, which pulls CO2 out of the atmosphere, combusting of fossil fuels, turning the carbon into a gaseous form and put it in the atmosphere. What are the impacts of that? We can measure solar input. We know and output, how it affects this planet. We can look at the changes, the Milankovitch cycles you're going to encounter very quickly here. We know what humans are doing in these climate forcings, again, by deforestation alone. We know that ocean acidification happens from the CO2 that is essentially absorbed in the ocean, much in the way you supersaturate the air where water is, and you can force CO2 into the water. Okay, so you can have a soda, so you can have what in the world? A Coke, as Southerners say. A pop, a fizzy, whatever you want to call it, whatever part of the world you're from. And then we look at these other effects, though, of habitat destruction. What does it mean? Most scientists are in agreement that we're going through a 6 apocalyptic die-off of animals and extinction. And the previous 5 that we've been able to measure, the most recent was about 66 million years ago, and that was the dinosaurs. But we know evolution allows for some of those things to come through on the other side as dinosaurs eventually evolved into bird species, among other things. Okay. That said, though, when we look at the impacts of why is there coral bleaching from what we're doing here, so a lot of the drivers are I think they're obvious to you, but then I think some of them might not be. So if we look here, just showing you how we measure stuff, collecting data, this EKG looking the actual concentration of CO2 in the atmosphere in parts per million. Why does it go up and down? Well, the northern hemisphere is loaded up with terrestrial trees that drop their leaves. They're deciduous, and they drop their leaves in the fall throughout the winter. So those trees aren't active, and so what happens to CO2 concentrations is they spike during the northern hemisphere winter. Well, why does it drop down again? Well, we go into spring and summer, and all those plants start pulling in CO2. But what do we have here is a mean line, an average line that shows us what? Well, a marked increase in CO2 in the atmosphere. We know what's doing it. Less trees to pull it out, more CO2 for industrial purposes. And so we see this again. So I wanted to show you this real quick, measured at Mauna Loa. We measure there, and a few years ago, about CO2 parts per million is that we crossed the 400 parts per million threshold. When this was made, it was nearing 2010, but I think escape here from the slide. I don't guess I can. Well, I'll try to show you at the end. Something's wrong here, and I can't pause it. But anyway, if you look at Mauna Loa and look at the atmosphere, you can see it's well over 400 parts per million now. I think I saw it. What I was going to show you is about 413 parts per million. So you could just check this at the Mauna Loa site. Okay, look at climate forcings real quick. I'm not about to teach you climate. I'm just showing you how complex some things can be. So look at the estimations of climate forcings. These are things that would make it warmer in red or cooler in these blues. And so overall, you'd see there's more red than blue. But we look at CO2 amount increased over the last, 250 years. This is methane right here, chlorofluorocarbons, okay? All these fluorinated gases that are out there. We talked about the ozone hole and use of freon and aerosols that we used for hairsprays back in the day that have now been negated. Nitrous oxide and ozone itself. We look here, though, at what are reflective aerosols. When these things are in the atmosphere, they kind of act like mirrors and bounce that incoming solar radiation back into space before it even becomes, an issue. Let's see what else. Just to let you know how complex this is, think about the climate forcing that is jet contrails. So those very high soaring jets that you may have flown on before burn fuel and water vapor comes out from behind them. Well, if they're very high in the atmosphere, it comes out as a crystalline structure of water vapor, which is actually just ice. Well, these little mirrors in the upper atmosphere do two things. They do reflect sunlight, which is the Earth's albedo, but they also, since they're water vapor, they hold heat. And so actually water vapor is a greenhouse gas. So you've got two things going on, and trying to get those figured out, it's really difficult. So the science is ongoing, but any good scientist would know what? Well, we'll know, we know how to measure this. We know how to test it. We're working on finding out how big an issue it is, but it's still within the realm of science, you guys, and there's checks and balances on this. So this is just a GIF or GIF file here showing you how, winter looks in the northern hemisphere. To orient you, this is Greenland. This is the southern hemisphere. This is Antarctica right here. But the snow cover, imagine how that changes, how much heat can be rejected or held. Vice versa. Look at these forests too. This is the Congo rainforest, the Amazon rainforest here. As the seasons move, you can see how this is stitched together satellite imagery, so this is not made up or anything. This is actual data that they've used from satellites. Anyway, or imagery they've used from satellites. But you can see that this thing is very dynamic. So one of the things we certainly know is that the ice caps are melting. We're still in an ice age. We're just coming out of it. We're coming out of it faster, though, because of what humans do. And so when we look at these things in geography, your textbook points these things out. We're looking at spatial aspects, the physical science perspectives, the environmental perspectives. So as you read through these chapters, take a look at some of the examples that they're using. For instance, absolute location. That's your first lab assignment where you're doing latitude and longitude versus relative location. You know, where do you live? Are you in a town? Are you in you know, do you live on the outskirts? Do you have a farm? When you look at this, you'd say, well, how does it relate to Nashville or to Vol State or something like that? When we look at spatial distributions and patterns, those are really big. This is spatial reasoning. Is it regular or is it random? Is it clustered or is it scattered? Like this, okay? So you've got here centralized and clustered as it intersects here. Decentralized, so you have many clusters. We look at all sorts of stuff in nature with plants and animals and the like. Is it dispersed? When we look at also animals, you know, we look, do they have enough habitat to thrive as a species? Are they connected enough, like the Florida panther, the mammal of Florida? We know it's going to go extinct because unless we keep them in zoos and self-breed them, because they're just too small in numbers and they're all disconnected because of humans and what they do. So when we look at the lithosphere, the solid earth, the biosphere, the life layer, the cryosphere, ice, hydrosphere, water, atmosphere, the air, and we look at that all together holistically, this is what we're seeing with, you know, calling this thing planet Earth. So again, looking at the systems and subsystems, just check these out, you know, drought cycles, desertification. We know that the Sahara Desert, guys, was green a long time ago. You can go and see pictures of, from National Geographic and others, the research that's been done here, of communities of people farming and living in the heart of that desert. We know that it's gotten drier over time, and this has happened naturally from the Milankovitch cycles. So take a look at those. Anyway, I'm going to close it here because I want to talk briefly about one other thing. So there'll be a part 2 to this. So I'm going to sign off on this one now, okay? Take care. See you in a bit. Bye.